Yeah, I'm Bill Bodell, and I'm really thrilled to present my work to you today about upgradeable proxy smart contracts and blockchains, which I worked on with my colleague at IIT, Sajad Meisami, and Professor Duan, who is now at Singapore Management. So this paper focuses on three main research questions. First of all, the importance of upgradable smart contracts. Second of all, variety. Third of all, and most importantly, security implications. So first of all, I want to just point out upgradable smart contracts and blockchains. They're here to stay. All of these protocols and many more, using them already. And more importantly, they do also introduce new security concerns. So a lot of recent bugs in upgrades that have introduced new bugs rather than fixing them. So we got to do something about that. You might be thinking, well, I thought the smart contracts were immutable. What is this about upgrading smart contracts? Well, it tends to revolve around a proxy contract, which stores the logic contract address as well as the setter to help update it. So in order to upgrade it, you simply deploy a new contract and then use that setter to change where that delegate call is going to get its logic from. Looking at this in a little bit more detail, you might have a user calling a function called inc, which, as another presenter pointed out earlier, has a function selector, the first 4 bytes of the hash of that function signature. And in the proxy contract, there is we use a special fallback function which catches any calls to an unrecognized function selector. And then that fallback function uses delegate call to fetch that logic from the logic contract, but most importantly, execute it in the context of the proxy contract. And so in the end, it is the proxy contract storage which is getting updated. So moving right along into our work, first of all, we started by creating a USC taxonomy. You might ask why we did that. Well, there's a variety of ways to implement an upgradable smart contract. All of the documentation is scattered and incomplete. And for a project like this, we really needed a systematic and comprehensive foundation so that we could build from the bottom up and make sure that we didn't miss anything. And so we start with the basic elements of a smart contract as defined in the Solidity documentation. And you can see in the first column of this table here, we take all of those basic elements and we extract all of the elements from those that are relevant to upgradability. And then enumerate all of the possible values of those specific feature sets. And so for an example, we can hone in on the setter, which is a very important feature set, and in particular, the definition location of that setter, whether it's in the proxy contract itself, a logic contract, or some other external contract. We take those low-level syntactic features and combine them into high-level semantic features. So continuing with that example, we can look at removable upgradability, which depends on that location of the setter. That we can say if it is located in the logic contract or some external contract that can be changed, then you can in fact remove upgradability. And then we take both those low-level and high-level features and we use them to construct our design pattern definitions. And so just to follow along with that, with those examples, I'll highlight the beacon proxy pattern, which is one in which the setter and the logic contract address itself are stored in an external third contract, which then can be queried by many proxies. And so you can use this pattern in order to simultaneously upgrade many proxies, which is very convenient. Moving right along, we developed this tool, USCHUNT, which was a fork of Slither. Why create a new tool? Well, state-of-the-art tools upgradability detection was wholly inadequate. Slither did checking for the word proxy or upgrade in order to determine if it was an upgradable proxy. There were no available tools to really classify USCs based on their features, and the security tools that do look at upgradability at all tended to focus on just a few well-documented issues. And so we developed USCHUNT, which adds a number of core components to Slither, as well as a number of plugins that we used in order to conduct our own study. And in order to do this, we also needed to tackle a couple of technical challenges like fixing inline assembly modeling in Slither, and adding Explorer querying so that we could fetch the source code for these additional smart contracts. And so USCHUNT takes as input that USC taxonomy. Of course, that's a one-time effort, plus the source code, and outputs a set of analysis results. And we evaluate our tool based on a data set of almost 1,000 smart contracts from the Ethereum mainnet after deduplication. Most of these, really all of them except for the few that we added ourselves, were originally identified as upgradable by Slither. 825 of these we could confirm through manual investigation as being upgradable. The rest were not, and we use this as our base, our ground truth to evaluate effectiveness. So USCHUNT correctly identified all but 13 of the upgradable proxies as being upgradable, giving us a false negative rate of just over 1%. All of those 13 false negatives were due to the logic and setter being located in an external contract, which we could not get through Explorer querying, say, because it was an unverified contract. Furthermore, we had a 0 false positive rate due to the stringent nature of how we defined it in an upgradable contract. So that was really great. We also evaluated efficiency and found that it took about 3/4 of a second on average to evaluate each contract, and over 83% of the contracts we could evaluate in under a second. So fairly efficient as well. Moving on to the important part, our findings. To answer that first research question set in terms of popularity and value over time, we had a broader data set, over 800,000 smart contracts across 8 major chains. And we found that about 1% of all of these contracts were upgradable proxy contracts. It's not including the number of upgradable logic implementations. And we also found that there was a rapidly increasing rate of these, particularly starting around this time in 2020. I think more importantly, to me at least, is the value locked in all of these proxy contracts is over $3 billion. So the key takeaway from this research question set is that not only are USCs rapidly increasing in popularity, but they also store a large amount of funds. Moving on to the second research question set on a variety of design patterns, I just want to point out a few findings here. So the first 3 columns are mostly older implementations of upgradability. Inherited storage and internal storage are not really recommended these days, and unstructured storage has been well standardized, so you don't really see many examples of non-standard anymore. You might look at EIP 1822 and think, well, that was really uncommon, and it was when we conducted this study, but that was over a year ago, and since then it's been rapidly gaining popularity for reasons that I'd be happy to talk with you about after the chat. Similarly, the diamond pattern, EIP 2535, has been slowly gaining popularity, but it's got a lot of critics as well. I'd be happy to talk about that as well after the talk. Finally, a couple of these patterns were really not defined anywhere in the literature, and so just want to highlight a few of those there. The main takeaway being that there are many ways to design a USC with many different behaviors, and not all of these are well documented. Finally, and most importantly, there are the security and safety concerns. So we found just over 2,500 security issues in this data set, a vast majority of which are to do with a class of issues that was not really documented anywhere prior to the study, which is insufficient compatibility checks in the logic setter. So I'll get into an example of that, but I also want to point out that there are kind of 2 broad categories of issues, implementation issues like the compatibility checks, but also policy decisions like using a time lock for upgrades, which can lead to vulnerabilities that cannot be patched immediately. So I'll show an example of that as well. First, on the subject of compatibility checks, we classified those into 4 broad categories, 2 of which are fairly sufficient. The best case is that you want to call some function in the new logic contract and verify that it does in fact return the expected value, and then at least to be sufficient, you should at least check that the new logic contract is in fact a contract, so check the length of the source code. An insufficient compatibility check might just check that the address is not 0, and that doesn't really say much about whether it is compatible or not. And finally, checking that the new address is not the same as the old address doesn't really have any bearing whatsoever on whether or not this is a good upgrade. I kind of wanted to stick on that slide for a second because you might also notice that there are a whole bunch of smart contracts in our data set which had no compatibility checks. whatsoever, just kind of counting on the developer knowing what they're doing. And so I'll show you one example from a prominent DeFi protocol, Synthetics, and you might look at this set target function and say, well, it looks like the target contract has to be this logic type contract, where logic refers to the contract logic defined below. However, from the perspective of the EVM, any contract type variable is interpreted as just an address. And so there really is no compatibility check going on here whatsoever. Target could be an externally owned account. Also, while we're on this example, I'll quickly point out one of the more well-documented issues, a storage layout collision, where both the target address in the proxy and the other address in the logic contract both occupies the storage slot 0. This was somewhat mitigated by the fact that Synthetics also uses a toggleable delegate call feature, which is another one of the features we define in our taxonomy. We don't show that here in this snippet, but basically they use a Boolean to determine whether they use delegate call or just a call. If they hadn't done that, then any call to this set other address function would have overwritten the target address in the proxy. And we informed Synthetics of this. They basically said, well, we're never going to use delegate call. So kind of it is what it is. Finally, want to show you an example of a proxy with a time lock. So you can see in this proposed function, they store the upcoming implementation address, but also the time 2 weeks from now when that upgrade can be pushed through. And then the upgrade function, this is how we identify this feature by checking for a require that compares the timestamp to the current timestamp. And while this is a policy decision, not a bug, it's worth pointing out nonetheless, because one of the more high-profile bugs introduced in an upgrade to Compound was exacerbated by the fact that the developers couldn't really do anything about it for 7 days while the upgrade was pending in this time lock. And so when additional funds were put into this vulnerable contract, they just had to sit and wait. So key takeaway here being that that upgradable smart contract developers need to be aware not just of implementation details, but also of policy decisions. And yes, I know that I have a meeting, but I don't think we're going to have that meeting today. Anyway, in conclusion, just going to quickly go through our contributions here. So we developed a USC taxonomy, as I showed you. We designed and implemented a novel static analysis framework on top of Slither. We conducted the first large-scale study of upgradable smart contracts with source code from over 800,000 contracts across 8 mainstream blockchains. And finally, we open sourced the entire implementation and the study data and artifacts, which you can find at this link below. And so thank you very much for listening. I'd be happy to answer any questions if there's time.